Imagine you have built a machine learning model. It works perfectly. You test it 1,000 times. It gets the right answer 99 times out of 100. You feel ready to launch it into the world. But then you deploy it, and within hours, everything breaks. Not because the math was wrong, not because the algorithm was flawed, but because the world changed while you were sleeping. This is the hidden crisis in artificial intelligence. We spend so much time talking about neural networks and deep learning that we forget the plumbing. We forget the pipes that carry the data from the real world into the computer. Here is the thing. We tend to treat machine learning as a product rather than a process. We think of it as a static tool that you build once and then use forever. But machine learning systems are living organisms. They depend on a constant flow of data. If that flow stops, or if the data changes shape, the system fails. This is not a bug in the code. This is a feature of the environment. The real world is messy, it is dynamic, it is constantly shifting. And our models are often built to expect a static snapshot of reality. Think about data drift. This is perhaps the most common reason models fail in production. In the beginning, your training data represents reality. You feed the model historical examples of what happens when a customer buys a product, or when a machine part is about to fail. The model learns the patterns in that data. But reality is not static. A pandemic changes spending habits. A new season changes weather patterns. A viral trend changes user behavior. The model learns a snapshot in time. When that snapshot ages, the model starts making guesses based on yesterday's rules. It is like a weather forecast that was perfect for January, but is applied in July. The numbers might still look correct, but the context is gone. The system is technically accurate according to its training, but practically useless because the underlying distribution has shifted. Now consider this. There is another failure mode that is even more subtle. It is called schema mismatch. This sounds technical, but it is actually a language problem. Your system expects a date in the format of January 1st, 2024, but the database sending the data decides to switch to the 24th of January format. Suddenly, your model cannot read the input. It is not a logic error. It is a translation error. The machine thinks the data is garbage because the structure does not match the blueprint. This happens constantly in large organizations. Different teams use different tools. One team updates their database schema without telling the machine learning team. The pipeline breaks silently. The model stops receiving valid input. It starts making predictions on null values. And nobody notices until the business metrics start dropping. And consider latency spikes. You might have a model that makes a prediction in 1 millisecond. That is incredible speed. That is the kind of performance that wins awards. But what happens when 10,000 people ask for that prediction at the exact same time? The network slows down, the queue builds up, the user experience degrades. Your model is still accurate, but it is too slow to be useful. In high-frequency trading or online advertising, speed is just as important as accuracy. If the answer comes 10 seconds late, it is worthless. This is a systems engineering problem, not a machine learning problem. It involves the central processing unit and the graphics processing unit. It involves the bandwidth of the network. It involves how the application programming interface handles the load. This brings us to the core tension in the field. Research papers talk about sample complexity and theoretical bounds. They promise mathematical guarantees. They tell us how many examples we need to train a model to a certain level of confidence. But those guarantees assume ideal conditions. They assume the data distribution stays constant. They assume the hardware does not fail. In the real world, these assumptions are often the first things to break. We are moving from a discipline of pure mathematics to a discipline of systems engineering. The field is characterized by a tension between increasingly sophisticated theoretical frameworks and the persistent need for reliable, interpretable application in complex, non-idealized settings. Furthermore, we are facing new challenges with large language models. These systems are powerful, but they are grappling with the hallucination problem. They generate text that sounds confident but is factually wrong. This creates a critical need for clear terminology and robust evaluation metrics to distinguish between probabilistic generation and factual accuracy. If a system is designed to automate analytical tasks and it starts inventing facts, the trust is lost instantly. We are seeing a shift towards specialized, high-performance frameworks to handle the increasing complexity. We are moving away from generic solutions to distributed systems that can handle the scale of real-world machine learning tasks. The ecosystem is rapidly shifting. Major tech companies are investing billions in infrastructure and tools to commercialize these capabilities. But the human element remains crucial. Sometimes the data is clean and the model is perfect, but the interface confuses the user. If a recommendation engine suggests something that makes sense statistically but feels wrong to a human, the system fails. We call this the human-in-the-loop problem. It is not just about the code working, it is about the code working for the person using it. The translation of these abstract guarantees into robust, real-world deployment in dynamic environments like networked business remains an unresolved challenge. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.